Okay, I'll continue now. So I can write v plus f of x is equal to v because f of x belongs to v. Now let me substitute the polynomial f of x here. So I get the coset v plus the polynomial equal to v. I can split this coset into sum of cosets as v plus a naught plus v plus a1x plus v plus ax square plus etc. v plus an into x to the power of n, and that is equal to v. As I told you in the earlier steps that we can remove this scalar outside and I can write a naught into v plus 1, a1 into v plus x plus a2 into v plus x square plus etc. an into v plus x power n equal to v. So now here this x is x to the power of 1, here it is x square and here it is x to the power of n. I can write this v plus x square as v plus x whole square because this is the coset v plus x into v plus x. So we get v plus x into x, that is x square. So I can replace this v plus x square as v plus x whole square. Similarly, v plus x power n is nothing but v plus x multiplied n number of times. So I get v plus x to the power of n. So this polynomial on the left hand side is the coset polynomial, which is having the element v plus x, right? Since it is v plus x and it is satisfying this polynomial and it is giving you the 0 element in k, therefore this v is the 0 of k. It follows that v plus x in k satisfies the polynomial f of x. Therefore, this v plus x is the root of the polynomial f of x in k. So, f of x as a root in k, hence the theorem. So, this ends the Kronecker theorem proof, right? So, next let us move on to the corollary to this theorem. So, it is a simple corollary. Within a few steps, we can write the proof. So here they have given that the statement states like this: if f of x is a polynomial of positive degree, which is similar to the statement of Kronecker's theorem over a field f, then there is an extension k of f such that f of x as a root in k and degree of k over f is less than or equal to degree of f of x. In Kronecker's theorem, it was equal to degree of f of x. Why? Because f of x was an irreducible polynomial. Here f of x is a polynomial. They haven't given any condition on f of x. It is a polynomial of positive degree. That's it. It is not given that whether it is irreducible or not. Suppose if I assume that f of x is an irreducible polynomial, then by Kronecker's theorem, we can find an extension k of f such that f of x has a root in k and degree of k over f is equal to degree of f of x, hence the result follows. Okay. This is true when f of x is irreducible. Suppose if it is not irreducible, that means it can be factorized. So when we factorize, we can think of one of the factor to be irreducible or both of them can be sometimes irreducible. So I can split this f of x as p of x into g of x. Here I am going to assume that p of x is irreducible in f of x. This can be done because we can factorize, still we get one of the factor to be irreducible, right? So clearly here degree of p of x, because it is a factor of f of x, its degree will be less than or equal to degree of f of x. Now let us use the theorem, that is the Kronecker's theorem for p of x now, because p of x is irreducible. I can apply the theorem for p of x. Now p of x being irreducible over f, by Kronecker's theorem, there exists an extension k of f such that degree of k over f is equal to degree of P of X. But degree of P of X is less than degree of F of X. Okay. So when you assume that P of X is irreducible, we can apply Kroneker's theorem and find an extension K of F such that degree of K over F, which is equal to degree of P, is less than degree of F of X. So first part is over now. So we have shown that degree of K over F is less than or equal to degree of F of X. But we need to show that F of X has a root in K. Okay. By Kroneker's theorem now, P of X will have a root in K. Right. Let us assume that root to be some alpha. So P of X has a root alpha in K. What do you mean by root? It satisfies the polynomial, that is P of alpha equal to 0. Now let us substitute this alpha for X in the expression for F of X. F of X was equal to P of X into G of X. Now for X is equal to alpha, we get F of alpha is equal to P of alpha into G of alpha. But P of alpha is 0. Therefore, P of alpha into G of alpha is equal to 0. So we get F of alpha is equal to 0. Since F of alpha is equal to 0, this alpha is satisfying F of X. Therefore, alpha is a root of F of X in K. So we get alpha to be root of F of X in K, as well as we have degree of K over F to be less than or equal to degree of F of X, hence the result of the corollary. Right. So we have proved the corollary. Now let us move on to the existence theorem. So existence theorem's proof depends on the proof of the corollary as well as the Kroneker's theorem. And in one step, we are going to use factor theorem. Right. Now let us see the statement. Let F be a field and F of X belong to the ring of polynomials F of X such that degree of F of X is equal to n and n is greater than 0. That means degree of the polynomial of F of X is positive. Right. So it is all the same in the statement of Kroneker's theorem or the corollary. Okay. Then there exists a finite extension K of F. This is also in the statement of the corollary of degree at most n factorial. This was not there. Degree at most n factorial is not in the statement of the corollary. But the rest of the things are there. That is, degree of K over F is equal to n factorial and F of X has n roots in K. There in the corollary we told F of X has a root in K. Here in particular we need to say that all the n roots of F of X are in K. Okay. So here what we do is we are using mathematical induction to prove the theorem. Okay. So induction is applied on the degree of the polynomial. Okay. So proof by induction on n, where n is the degree of the polynomial. So in the first step, we take n to be equal to 1. That is, degree of F of X is equal to 1. Since degree of F of X is equal to 1, F of X can be expressed as Ax plus b. Since F of X is equal to Ax plus b and it is of degree 1, coefficient of X, which is A must be not equal to 0. If it is equal to 0, then the degree of the polynomial is not equal to 1. Okay. It becomes a 0 degree polynomial. So for some A and B belongs to F. Since A is not equal to 0 and F is a field, A inverse exists because every non-zero element in a field has a multiplicative inverse. So A inverse exists. So in this case, here we need to show that there is an extension K of F. So here we are going to take that extension to be F itself. F is an extension of F. So F over F is equal to 1 and it is of degree 1 factorial. We need to show that it is n factorial. So here 1 can be written as 1 factorial. And X is equal to minus B into A inverse. So this is an element of F. Let us take that to be the root of the polynomial f of x. Suppose if I put x is equal to minus b a inverse here, I'm going to get 0. So this is the root of the polynomial f of x, and this belongs to the extension f. Hence, the theorem is true when n is equal to 1. Okay. Now, the assumption step or the hypothesis step. Let us assume that the theorem is true for all polynomials of degree less than n over the field f. So, for all polynomials whose degree is less than n, the statement of the theorem holds good. And we are going to prove for degree n. Okay. So, let f of x be a polynomial of degree n over f. So, this implies there exists an extension k naught of f such that f of x has a root alpha in k naught. How can you write this? This is possible by the previous corollary. So whenever f of x is a polynomial of degree n over f, we have shown that there exists an extension of f such that f of x has a root alpha in k naught. Okay. So what can you say about degree of k naught over f? It must be less than or equal to degree of f of x, and degree of f of x is equal to n. Therefore, degree of k naught over f is less than or equal to n. So this we can write using the previous corollary. Okay. Now f of x is a polynomial of degree n and it has a root alpha now. Let us use the factor theorem now. Since f of x has a root alpha now, by factor theorem, there exists a polynomial p of x in k naught of x, that is the extension of f, such that f of x is equal to x minus alpha, because alpha is the root, into the polynomial p of x, where degree of p of x is equal to degree of f of x minus 1. Degree of f of x is n, so degree of p of x becomes n minus 1. So this can be written using the factor theorem. This part we can write using factor theorem. The earlier part using the corollary. Now the degree of p of x is equal to n minus 1, and this n minus 1 is less than 1. Sorry, less than n. Since this is less than n, I can use the induction hypothesis or the assumption which I have done. That is, the theorem is true for all the polynomials whose degree is less than n, right? Now we have a polynomial whose degree is less than n, so I can apply the result of the theorem. So p of x being a polynomial of degree n minus 1 over the field k naught, by induction hypothesis, there exists an extension k of k naught of degree at most n minus 1 factorial. Why n minus 1 factorial? Because the degree of the polynomial is n minus 1 factorial. And p of x has n minus 1 roots in k. So when I apply the result of the theorem, that is the assumption, I can write this. There exists an extension k of k naught of degree at most n minus 1 factorial, such that p of x has n minus roots in k. So how many extensions we have now? Here we took a k naught, an extension of f, and now k an extension of k naught, right? So k naught being a finite extension of f, k being a finite extension of k naught, by transitivity property, we can write k over f is equal to k over k naught and k naught over f. And degree of k over k naught is at most n minus 1 factorial. Okay, so it is less than or equal to n minus 1 factorial. And degree of k over n was less than or equal to n. So we get n minus 1 factorial into n. So this gives us n factorial. Therefore, k over f has a degree less than or equal to n factorial. Therefore, we can say that k is a finite extension of f of degree at most n factorial. And what do you know about f of x? F of x has n minus 1 plus 1 equal to n roots in K. What are these n minus 1? N minus 1 is P of x. And whatever P of x has a root, that will be a root of f of x, because f of x is equal to x minus alpha into P of x. If any root satisfies P of x, f of x also becomes 0. Therefore, n minus 1 roots of P of x are roots of f of x. And we had one more alpha as the root of f of x. So plus 1, it gives us n roots in K, because every root of P of x is a root of f of x. Hence, by induction, the theorem follows. So this is the proof of the existence theorem. Next, I am going to define this and end up the session. Simple extension of a field f. This we have seen, that is an extension K of field f is called simple extension of f. If you can write K is equal to f of alpha for some alpha belonging to K. So we have seen examples, that is Q of root 2, right? It was an extension of Q, and that is simple, okay? And here, this alpha which we have taken here is known as the primitive element. So whenever K is a simple extension of f, such that K is equal to f of alpha, where alpha belongs to K, this alpha is known as primitive element, right? This is the first definition. And the other definition which I want to say is root field of a polynomial. So a simple extension K of f is said to be root field of an irreducible polynomial. Here we are treating irreducible polynomial f of x, which belongs to capital F of x if K contains a root of f of x. If K contains a root of f of x, then K is said to be root field of f of x. Okay. So let us see one example, a small example here. The irreducible polynomial x square minus 2 over q. Over q it is irreducible. It is not irreducible over r. Okay, it will be reducible over r. X square minus 2 equal to 0 implies x is equal to plus r minus root 2, and this root 2 doesn't belong to q. But this root 2 can be taken in q of root 2, which is the extension of q. And this is a simple extension of q and contains the root 2 of x square minus 2. Therefore, this q of root 2 is the root field of x square minus 2 over q. So, whichever extension field contains the root, that extension will become the root field or the root field of the polynomial x square minus 2 over the field q, right? So this is the example for root field polynomial, okay, and primitive element and the simple extension of the field f, okay.